In this video, we want to talk about the heart of the matter. What is Lenz's law actually leading to? What do we actually care about? And that thing that we care about is that this induced current is caused by an actual EMF, an actual induced voltage in this circuit that seems to be caused from nothing at all, except for a changing, moving magnetic field, right? So how can we actually calculate what this induced EMF, in other words, this induced voltage will be, so that we can actually design power plants that send this electricity off at the right voltages to our power lines? Well, turns out, very, very simple. This induced EMF, remember it's this symbol E, right, is equal to negative the change in the magnetic flux over the change in time, okay? On the slide here, you can see that it's actually shows the calculus version, the differential version. It's really the same thing, but this is, allows for small infinitesimal incremental changes in flux. Now, when I say that the flux is changing, what does that really mean? It really means that any one of three variables could be changing, as we talked about before. Right? So when you're solving for the EMF in Faraday's law, I'll put my little minus sign there. When you're solving for the EMF in Faraday's law, you need to take a look and see what's actually changing. Is it the B field that changes in this interval of time? Is it the area that changes in this interval of time? Or is it the angle that's changing in this interval of time? Because that's obviously important because we have to take account into which variable is actually changing and how much is changing by in order to calculate how big the induced EMF will be. All right, so how does this work? Before we get there, I want to add one little wrinkle, and that is that this here is in the case of one loop, right? But what if you have a coil that's a whole bunch of loops, like this? Okay, well, it turns out that there's an induced EMF for every single one of these loops. It accumulates, it multiplies, right? So in other words, that means that the true equation for this induced EMF is delta NBA cosine theta, where n is the number of turns in the loop, all right? So for example, in these coils for generators in power plants, you actually have many, many loops in these coils so that you actually get a nice, strong, solid induced EMF. All right? So if we're to replace all of this with one equation, right, to find the induced EMF for any kind of a changing flux, it really is, the induced EMF is negative n delta BA cosine theta over delta t. All right, so let's see how this actually works in real life. All right, let's take a look at a question involving an MRI machine, okay? Because MRI machines actually work using this principle of electromagnetic induction, okay? And the loops that you're talking about are little conductive loops of muscle tissue. So the body is a conductor. So rapid magnetic field changes in an MRI machine can induce currents in the body. To estimate the size of these currents and any biological hazard they might impose, consider a loop of muscle tissue. This might be muscle circling the bone of your arm or thigh. Although muscle is not a great conductor, its resistivity is about 1.5 ohms per meter, or ohm meters. So we can consider it to be a conducting loop with a rather high resistance. Suppose the magnetic field along the axis of the loop drops from 1.6 Tesla to 0 Tesla in 0.3 seconds. What is the largest possible rate of change, which is the largest possible rate of change for an MRI solenoid? What would be the induced voltage in that loop? Okay? All right. So here's the thing, okay? We first look at this equation and ask ourselves, in this problem, which of these three factors is actually changing? I'll give you a second to piece it together. I'll give you 3 seconds. Anyways, it looks like the problem is telling us that the B field, the magnetic field, is changing from 1.2 T to 0 in 0.3 seconds. okay? And we're talking about one loop. So if we are going to start applying the math of this, right, we have one loop, so we can just drop that n, right? This minus sign, this is just a way of saying that the induced EMF opposes the change in flux. I wouldn't really worry too much about this minus sign. There'll be very few questions where I will actually ask you to include the minus sign, but I will ask you to know the direction of an induced current like we did with Lenz's law in the last few videos, all right? So I'm going to take this away for now, all right? And I want the change in B field, right? So basically, there's a change in B over change in time, right? And the rest of the stuff is constant. The A cosine theta is constant, right? And we're assuming in this problem that the magnetic field is actually perpendicular to the loop as is shown in that picture, right? The loop is this way. And so the area vector of the loop is this way and the B field is this way. So in other words, we can just say that this is 0 degrees, right? Which makes that just 1. So in other words, our change in B is 1.6 to 0, right? So that's 1.6 minus 0 over 0.3 seconds times the area, okay? Now, this problem does go ahead and give us the diameter of these muscle loops, okay? It says the diameter of a muscle loop is about 8 centimeters, which means the radius is 4 centimeters, or 0.4 meters. So this area then becomes pi times 0.04 squared. Right on? Perfect. Okay, and if I put that in my calculator, what do I get? Well, I get a value of 0.027 volts. Okay, so it's not a lot, right? We're talking 27 millivolts, right? But that is enough for the MRI machine to be actually detect that voltage, detect the current that results from that voltage. All right? Speaking of the current that results from that voltage, how do we calculate that? Well, we need to use the resistivity of the muscle tissue, right? So here's the deal with that. We know that resistivity is equal to rho times length times area, right? And so this is the actual length of the loop. In other words, the loop is a circle, so that's going to be the circumference of the loop, right? Divided by the cross-sectional area that the loop's made out of, right? So it looks like here they actually give us the diameter of the loop itself, not the diameter of the actual circle, but the diameter of the material, the muscle that it's actually made out of. That is 1 centimeter. So that radius is 0.5 centimeters. So they tell us the resistivity is 1.5 ohm meters, right? The length is going to be 2 pi r, right, or pi d, but 2 pi r is the circumference of that loop, so that's 2 pi times the radius of the loop itself, right, which is 0.04 meters, or 4 centimeters, right? And the area is the actual area, as you can see in this picture, of the material itself, which is going to be pi times the diameter is 1 centimeter, so this is 0.005 meters squared. Whew. Okay, that means that I am getting a resistance for that little muscle loop of 4,800 ohms. Okay, and if we want to find the current then, using this induced EMF, all right, we simply then use Ohm's law, just like we did in the last exam, okay? And we say that I is equal to the induced EMF over R. The induced EMF is 0.027 volts, right? And the resistance is 4,800 ohms, right? Which means the induced current in this little loop of muscle that's detected by the MRI machine that allows you to image you know, this hole with your face or whatever you're MRIing, right? That current will be 5.6 times 10 to the minus 6 amps. Okay, check me on that. Make sure my calculations are kosher. But otherwise, we have done our first Faraday's law problem. In other words, we found the change in flux, which in this case is caused by the change in magnetic field, right, over a certain amount of time, which in this case was 0.3 seconds. We calculated the area of this little loop of muscle. It's pi r squared, where r is 0.04 meters or 4 centimeters. We found the voltage, and we used Ohm's law, V equals IR, to find the current through that loop given that voltage. And that current is the induced EMF, which is just this, divided by the resistance, which we calculated using our old, dependable, famous resistance formula. All right? You see, nothing too crazy and new here, but we have found a way to calculate currents that aren't actually caused by batteries. They're just caused by changing magnetic fields. Pretty cool.